All right, so to start our discussion of angular momentum, let's actually go back and look at our analog quality from translational motion, linear momentum. So we talked about the linear momentum of a particle, right? P is given by mass times the velocity vector. So we define momentum to be a vector quantity which points in the same direction as the velocity vector. For us, because we work mostly two-dimensional problems within introductory level physics, we said fine. This means that we've got an equation for the x component, an equation for the y component. And in both cases, what we're going to do is we're going to break up the velocity vector into its x and y components multiplied by mass to get the x and y components of the momentum. So the angular momentum of a rigid rotator, let's start there, is going to be given by a very similar equation. So notice we've swapped out the linear momentum for the angular momentum, and we use L to represent the angular momentum. Mass has been replaced by the moment of inertia. Linear velocity has been replaced by angular velocity. Again, we've still got a vector equation that tells us that angular momentum is a vector quantity which points in the same direction as the angular velocity vector. And since we're going to spend most of our time with objects in the xy plane, then what we'll be thinking about is how they rotate about the z-axis. So our angular momentum typically is going to be thinking about the angular momentum in z. And since this would be a one-dimensional problem in terms of the angular momentum, means that we will focus on the signs. So making sure that we have the right positive or negative sign to go with the angular momentum based on whether it's a positive or negative for the angular velocity. So if I think about I got a uniform long thin rod that's able to rotate clockwise about its center of mass. So there it goes. Well, I know from my right hand rule that if I take the fingers of my right hand and curl them clockwise, my thumb has to point into the page, so that tells me that the angular velocity points into the page. And our equation tells us that if the angular velocity points into the page, then the angular momentum also has to point into the page, because those two things point in the same direction. So in terms of the units of angular momentum, I know that the units of angular momentum will be given by the units of moment of inertia times the units of angular velocity. Moment of inertia has units of kilogram meters squared. Angular velocity has units of radians per second. And what you notice here is, again, we talked about sort of the special property of radians as a unit, that it is there when we need it and kind of disappears when we don't. And this is one of those situations where basically it disappears. So my units for angular momentum are kilogram meters squared per second, and I don't worry about adding the radians. So we're just going to use kilogram meters squared per second as our units of angular momentum. Now, when we first introduced linear momentum, we did it in relation to the translational version of Newton's second law. We said, well, Newton's second law says that the net force is equal to mass times acceleration. Since acceleration is the derivative with respect to time of the velocity, I can take that mass, tuck it back inside the derivative, then I've got the derivative with respect to time of mass times velocity, and that's the linear momentum. So the net force acting on my object is equal to the time rate of change of the linear momentum. And so what this means is if the vector sum of the forces that act on my object is 0, so this term is 0, then this term must also be 0, which tells me that that my linear momentum doesn't change, which is another way of saying that the linear momentum of your object is constant. If I start with the rotational version of Newton's second law, which again tells me that the net torque is equal to the rotational inertia times the angular acceleration, we can play the same game. So we can take the angular acceleration, we know that's defined to be the derivative with respect to time of the angular velocity. And if I take my rotational inertia and tuck it inside the derivative, then I've got the derivative with respect to time of I omega, and that's just another way of saying the angular momentum. So this tells me that the net torque is also equal to the time rate of change of the angular momentum. So this tells me that the vector sum of the torques, if I add up all the torques acting on my object and they add up to be 0, then the angular momentum of my object is constant. Again, if this term is 0, then this term also has to be 0. And so the momentum of my object doesn't change because its time rate of change is 0. Now, what we've done so far also works for a particle, but it's often easier with a particle to calculate the angular momentum in a different way. So for a particle, we can calculate the angular momentum as r cross p. So again, we're taking the r here is the position vector of the particle, so it's going to run from, basically you're treating the pivot as the origin, and so you're going to run a vector from the pivot to the particle's location. I know that the momentum of the particle, the linear momentum, points in the same direction as the velocity. So when I think about dealing with this cross product, just like any cross product, I can say, well, the magnitude of this, of the angular momentum, is going to be given by the magnitude of this position vector times the magnitude of this momentum vector times the sine of the angle between them. So one thing I can do is I can deal with this momentum vector, saying it's going to be mass times the speed, right, the momentum of the velocity vector, or the magnitude of the velocity vector. And then I've pulled those two out front, and I've left this r sine theta here at the back side. And so the first thing I need to do is figure out what theta is. So again, here is theta. It's the angle between r and v when I draw them both from the same point. So if this is the angle here, well, it's got to be the same angle here. And so r sine theta is just the opposite side to this angle. And so you notice here is that distance r sine theta. So what this tells me then is that only the component of the position vector perpendicular to the particle's momentum matters in calculating the angular momentum. So my linear momentum here points up, so I'm only interested in the horizontal component, i.e. the component that's perpendicular to the linear momentum when I'm thinking about the angular momentum. Now another way to deal with this is to talk about the line of motion. So this is similar to what we talked about when we were dealing with torque and we talked about the line of action, where we said the line of action was the line that the force vector lies on. Well, the line of motion is the line that the velocity vector or momentum vector lies on. So here, notice the line of motion basically is the line that our velocity points on. So in this case, it happens to be vertical. And then I can think of the angular momentum as being mass times speed times this distance L, where L is defined to be the perpendicular distance from the pivot to the line of motion. So notice that L here gets me exactly the same length that r sine theta gets me. So either way, in terms of thinking about the angular momentum, either way of doing this calculation, they both have got to give us the same answer. Now, thinking in terms of this perpendicular distance L does raise an interesting question. So what if I have a particle moving in a straight line? Right? Our previous picture, we had a particle moving along a curve, and it seems reasonable that something that's moving, that's rotating as it moves, has an angular momentum. But what if I have a particle that's moving in a straight line? Does it also have an angular momentum? And the answer very much depends on where the pivot is located for your problem. So let's say I have a car, and then I have three different observers, an observer at A, an observer at B, and an observer at C, that are going to watch this car move to the right at a constant speed. So there's my car, it goes to the right, so there's its velocity vector. So what I'm interested in is for which observers does the car have an angular momentum that's not equal to 0? And again, thinking about the way we finished up on the previous slide, it's easy to draw in my line of motion, right? That's the line running to the right. And then if I think about that perpendicular distance, well, for my observer at A, its perpendicular distance will be here. So here's the L. So it would be mass of the car times speed of the car. That's the same for all three observers. A has this perpendicular distance to the line of motion. So mv times this L would give me the angular velocity, the magnitude of the magnitude of the angular momentum as measured by an observer at A. B, I notice that the line of motion runs through point B, so L at B, for the observer at B, that perpendicular distance happens to be 0. So for an observer sitting at B, that observer would basically say that the car has no angular momentum. For an observer at C, again, here's the perpendicular distance to the line of motion for an observer at C. So here's a situation where the observer at C would see an angular momentum given by mass of the car times the speed of the car as it moves times this perpendicular distance. So here you see that 2 of the 3 observers do measure non-zero angular momentum. The observer at B says that the car has no angular momentum. And the thing that's interesting is if you think about the observer at B, right, the observer at B can watch the car without having to turn his head to watch it. For an observer at A, they've got to turn their head to watch the car. For an observer at C, they've got to turn their head to watch the car. So one of the things that this is sort of indicating is that if your head has to turn to watch a particle move, then you're going to measure that particle as having a non-zero angular momentum from your location. So your location then becomes the pivot, and then when you think about the angular momentum, if you've got to turn your head in some direction, and again, the axis around which you turn your head is going to give you an indication of the direction of the angular momentum. But if you've got to turn your head so that you can watch the particle move, then you're going to measure an angular momentum that isn't zero for that particular particle.